Let's take a look at an example of a Lagrangian optimization problem. So this is a situation where we have something we want to maximize. In this case, we're going to try and maximize output. So we got our production function, but we're maximizing subject to a budget constraint. So our budget, we're going to set to 108, let's call it $1 million. We got $108 million. The price of capital, we need 3 million for every unit of capital and 4 million for every unit of labor. The million here is just to make it more exciting, but really it's 108, 3, and 4. So let's start by putting those into a budget constraint. So our budget is going to be R times K plus W times L, right? Or price of capital, price of labor. Which means we're looking at 3K plus 4L equals 108. So this is going to be our constraint. So we're going to maximize this subject to 108 is greater than or equal to 3K plus 4L. All right, the order doesn't matter a whole lot. All we're saying is we've got at least as much budget for the amount of money we spend on capital plus the amount of money we spend on labor. So now we're going to set this up. We're going to create a Lagrangian function, which I normally do with this fancy looking L, which is a function of Q and L, or sorry, of K and L. In this case, we're going to set this up as K to the 0.4, L to the 0.5. This is the first part, right? This is the thing that we're trying to maximize. Let me just break this up a little bit. And then we're going to add on this new term plus lambda times our constraint. Now, for our constraint, we're just going to rearrange this. So this is the same as saying 108 minus 3K minus 4L is greater than or equal to 0. And we're just going to call it equals 0 because we're going to assume that we're on that budget constraint. That's just going to make it a little bit easier to do the math, right? So this, if this is all equal to 0, then when we put this in here, 108 minus 3K minus 4L, if we're on the budget constraint, then this whole thing becomes 0, and what we're going to end up with is just what is our output, right? Otherwise, we're going to have something like we don't use all of our K and L, right? So if we've got extra budget, if we have a greater than rather than an equals, in that case, we're going to have some term in here, and our lambda term representing our shadow price is going to end up being 0. But let's not worry too much about that. Let's go ahead and set up, well, we've set up the problem, right? So we've got our objective function. Now we go through our basic procedure. So how does L change as we change K? Well, we bring down this term, right? Let me make sure I'm thinking about this right. So we get 0.4 times K. 0.4 minus 1 becomes minus 0.6 times L to the 0.5. All right, so far so good. Now this part becomes a little bit trickier, so let's just lay this out a slightly different way. Lambda 108 minus lambda times 3K minus lambda times 4L. All right, so I'm just kind of expanding through here. So 3K times plus lambda is that. That's going to make it a little bit easier to get what is our partial derivative of this whole thing, right? This is just a rewrite. We're not adding it on top of this. But what is the partial derivative of this whole thing with respect to K? Well, there's no K term here. There's no K term here. So we're going to have a minus lambda times 3 times K to the 1 minus 0, which is, or sorry, 1 minus 1, which is K to the 0, which is 1. So this all boils down to minus 3 lambda. And of course, we are going to set that up to be equal to 0. when we are maximizing, right? So now we're at the part where we're introducing those first order conditions where we're normally looking for our function flattens out. Now we've got this lambda term here, which basically means either we're flattening out because of k and lambda, or sorry, k and l, or we're flattening out because k and l and this thing that's going to contain some information about our constraint. All right, but let's keep going. So L, fancy L sub L, how does big L change as we change our labor? And this, we're going to get 0.5. I'm going to stick with k to the 0.4, get this in order, times L to the minus 0.5 minus 4 lambda equals 0. Right? Not too bad. Partial derivatives are just derivatives. And finally, L of lambda. Well, there's no lambda terms in here, so that all goes away. We're basically going to be left with just this constraint. 108 minus 3k minus 4L equals 0. All right, so what can we do with this? Well, ultimately, we're going to do some rearranging. So let's go ahead and think about, let's go ahead and take these, right? We're going to have some stuff to divide out of this. I'm going to move these lambda terms to the outside. So I'm going to get 0. Basically what I'm going to do is along the lines of L sub k over L sub L. Kind of, I'll put a little tilde over top of these to indicate that I'm not literally dividing these. I'm going to do a little bit of a modification. So what have I got? I've got, and actually, you know what? Let me just change colors just to make it clear. So we're just doing algebra at this point. All right, so 0.4k to the minus 0.6 times L to the 0.5 is going to equal 3 lambda over 0.5 times k to the 0.4 times L to the minus 0.5 and then 4 lambda. Right, so we're just skipping a step here, but we're moving this term and this term over to here, and then we're dividing these two equations. So what have we got? 0.4 over 0.5, well, that's just the same as 4 over 5. K to the minus 0.6 over k to the 0.4, well, that's the same as 1 over k to the 0.6, right, which multiplied by 1 over k to the 0.4 means that we're just looking at a full k term down here, and then this one we're going to flip up. We're going to add positive 0.5, right? We're basically saying we're going to move this guy up here as 1 over this L to the 0.5, flipping the side of the fraction. Likewise, this guy we just moved down to a k to the 0.6. We got rid of that negative sign, and we got something that matches up pretty nicely. And then all of this, well, those lambdas cancel out, and we've got 3 over 4. So now we're able to rearrange and say what is k in terms of L and vice versa. So let's see, what can we do? Let's multiply that across, multiply this across. This is going to be L over k equals 3 times 5 over 4 times 4, 15 over 16. So basically for every 15 units of L, we expect to use 16 units of K wherever it is that our solution is happening. So if we just plug that right back into here, then things will be fine. Now, I should take a step back and say we're kind of glossing over questioning the second order conditions. Right, so when we saw three-dimensional optimization, we wanted to make sure that we were in fact looking at a maximum. In this case, the setup of the problem, I've chosen this problem so that we don't have to worry about that. For a Cobb-Douglas, this works. Another thing I'll point out is we're saying plus lambda times this stuff. I always forget whether we're adding or subtracting when I'm doing this in practice. And what ends up happening as a result is that, when we plug these numbers back into here and solve for lambda, maybe we accidentally get a negative sign, right? But it really doesn't matter that much. So if we get a negative sign, then we just sort of flip that in our head and reinterpret. All right, so what do we do with this? Well, now we can just plug these numbers, or use this ratio to solve all this stuff. So let's just go ahead and use our budget constraint. That'll be a little bit easier to work with. We'll switch to orange. So we got what? 108 equals 3k. Okay, so if we multiply this over, right, so if we say L over k times k equals 15k over 16, so we can say equals 3k plus, we can swap out this L for this L, so 4 times 15 over 16k. So now we got the budget just in terms of k, and we know that L is going to be 15/16 of whatever it is we solve for here. So what have we got? 3k, 4 over 16. Can we simplify 4 divided by 16? That's going to be just 1/4. So this is going to be 15 over 4 times k. So I'm going to end up with a 4 down here. So I'm just going to say, what is 4 over 4? Right? What is 1 times 3k? That's not going to be a big deal. Plus 4 over 16, like we said, is 1 over 4 times 15k, or k times 15 if you dyslex like me. And now, since we multiply by 4 over 4, we've got this denominator we can work with. So 4 times 3 is 12k over 4, right, which is just 3k, plus 15k over 4. 12 plus 15, that is what, 27k over 4 is 108. All right, 4 times 108, I'm just going to crunch this all into the corner. 4 times 108, that is 4 times 10 would be 440, minus 4 times 2. Right, so this is just 110 minus 2. Right, so 2 times 4 is easy. 110 times 4 is easy. So that is 440 minus 8 is 432 equals 27k. K equals 432 over 27. Let's see, is that something that's going to add up nicely? Let me check my calculator real quick. 432 divided by 27. I'm getting 16. Look at that. Nice, easy number. And hey, even better than that, we know that L is 15/16 of however much we use, however much K we use. So this means L must be 15. All right, so we found the mix that we want. Right, so we are going to maximize at L15, K16. Now, let's just go back and see what lambda is going to be. So, let's see, we've got a lambda term here. Well, let's do it like this. I got my calculator handy that I can show on the screen. Calculator. All right, so K is 16. 16 to the power of, whatever, I'll do to the power of 0.4. 0.4, so 3.03 times 0.5, well, it's the same as divided by 2. Let's just make sure that we've got the parentheses in the right spot. Divide by 2, and then times, or really, I guess, divided by L, what is it? So just the square root of L. right? So let's divide by the square root of L, which is just 15. And so I've got this whole term, right? Now this is the slope with respect to L of our function. So if we're thinking about more K, more L in this direction, we're asking around this point, what is the slope with respect to L? And that's saying we're increasing our output just a little bit, right? So we've got a slight upward slope around this point. So that has to be offset by this, right? So this term here equals this number, minus 4 lambda equals this. So this equals 4 lambda. So if we just divide by 4, that's going to tell us lambda. So lambda in this case is pretty close to 0.01. What does that mean? That means that if we loosen our budget, basically if we add $1 to our budget, we expect to be able to produce about 1/10 of an extra unit. Right? That's what the shadow price is telling us. Right? It's telling us what happens if we loosen our budget. So we get a result of, if we wanted to, say, go from producing however much it is we do produce, which is what we would get plugging these numbers into here. Right? Let's just go ahead and check that as long as we're here. 16 to the power of 0.4 times 15 to the power of 0.5 tells us that we are at our budget producing 11.74 units, right? Or maybe that's millions of units, whatever the case is. But if we add a little bit to our budget, then we are going to expand that by about 1/10. Let's just see how big that is as a percentage. That's not right. Doing this in the wrong order. 0.09 divided by all that stuff. So that's what, about 0.7%, right? Which is maybe not huge sounding, but for 1 out of 108, that's basically a little less than 1% increase in our budget and not quite 1% increase in our output. All right, cool. Now, something that you might do with this to play around with in your notes, maybe you plug into Wolfram Alpha, maybe you plug it into Excel, or maybe you just plug and chug different numbers with your calculators. But you'll see 0.4, 0.5, these are adding up to a little bit less than 1. So this tells us that we have something with, what's the word I'm looking for? My brain's falling apart this morning. We are getting not increasing returns to scale. We're getting decreasing returns to scale. So if we double things, we're going to double our inputs, we're going to get less than double our outputs. In any case, we have found a solution. We've walked through the Lagrangian. The most important part of this, let's go ahead and highlight as we wrap up. The most important part is getting this set up. Now, getting the plus lambda times this, or if we did a minus lambda times this, we'd have a negative sign where we shouldn't, but it's ultimately going to boil down to the same thing, right? So if we imagine that we've done a minus sign here, this would become plus signs here, and then this would become minus over minus, and we'd still solve for L is 15/16 of how much K we use. So we're still going to get to the same answer of what inputs we want. We would just need to do an extra step on the interpretation of the value of lambda. We'd get negative 0.09 for these numbers. In any case, that is a walkthrough of a Lagrangian optimization example. As usual, if you've got questions, ask in the usual places. Let me just really quickly draw this out. So if we've got L over here, K over here, our price of labor is a little bit higher. So I'll draw this like this. So here is very roughly what our budget constraint looks like. And we've got some isoquant, and we found, what do we say, 16 and 15 is where we are maximizing our output. Another good thing that you might do to just really hone in your skills with implicit differentiation is verify that when we do implicit differentiation on this, our value for dkdl equals the slope that we would get from our budget constraint, which should be, what, -3/4. In any case, ask questions if you got them, and I will see you in the future.